Hello, welcome to Chem 520 Concepts of Analytical Chemistry. We started January 7th. We'll be going through March 3rd. This is online. My name is Dr. Terry Villarreal. It's a pleasure to meet you. These videos are for week 1, January 7th, 2021. First, let me just apologize for the delay in these videos. As you know, we had quite the scene in our nation's capital earlier this week. I'm not going to get into that because I feel that that is outside the purview of our class. Just ask that you pray for the people involved and recovery for those that were hurt in the incidents. For those of you that don't know, I have worked at GCU for a number of years. I used to teach on campus, but now I teach online. I currently teach in Washington, D.C. I'm working from home. Since I'm very close to DC, the last week has been rather nerve-wracking, having to take care of a few issues and things like that. But hopefully now everything should be, I hope, relatively normal. My goal is to post these videos for our lectures on Thursday every week at the start of the new week. That way you have a chance for the whole week to look through them. These are going to include the main concepts. So I'm going to go through some of the more important things and try and work through a couple practice problems so you guys can get a feel. And we'll go through some of our main things right now. So first up, as I go through here, class overview. I will upload YouTube links because, trying to upload videos on GCU servers is not great. So I just use YouTube links. You will have found this on a YouTube video. Hopefully you should be watching it. And it's going to have the major points. I'm going to include practice problems, and I will typically upload the answers later so that you get a chance to work through them and you're not just like, I want you guys to try and work through the problems on your own. You have 2 forum posts every week. So basically you'll have 2 questions that are being asked. If you've done online classes before, you know how this works. You need to respond to each of those forums. They're going to be general questions. And then you need to make 3 more unique responses on 3 separate days. So a post a day, essentially. And the way I find to do this helpful and to help you guys out, I typically ask an extra question in the forums. So if you notice for this week, you have your first question, which I believe is about the scientific process. And then in there, I asked the second question saying, what's your favorite lab? And I think I've seen one of the students has responded. And so this is what I try to do so that I give you something. So you can come in, like say on a Thursday, Friday, Saturday, put a post to something, respond to stuff, whatever. Meet your 3 unique ones. Plus, don't forget the 2 that you have to do. So you're making a total of 5 responses. All right. So there's an announcement about this in case you're still a little confused. I'm always open to online meeting. Everyone is across the country, so trying to have set office hours doesn't work. Because I think I saw a student in North Carolina. So if you're in Arizona, that's a 2-hour difference. So basically what I like to do is just make office hours. Just send me a message. I can meet with you. We can do Zoom. We can do any other form of online meeting that you prefer to do. And I can work through practice problems. I can help you with stuff. And really, I'm available. So just ask if you need help. Go to the questions to the instructor forum if you want to ask a general question. Maybe one of your fellow classmates can help you. Message me privately if it's something a little bit more personal nature you just don't really want people to see. Send me an email and just let me know. I posted my phone number. It's there for you. I would say try to use the email and other forum. But if it's an emergency, say you're having a power outage or your internet's gone down, anything to where you will not be able to do something and it's then, feel free to use that phone number then. We're all adults, so I trust you guys will know when it's appropriate to use that. Just, use your best judgment. And then if you come into a help session, like say you want to meet and you want to talk about homework, I typically will ask you permission if I can record it. Then that way I can upload it to YouTube. So then, the questions you had probably had by other people as well. Right. And so as always, just ask away. I'm very excited. I graduated from the University of Washington with my BS in biochemistry, and I earned a PhD from Purdue University in organic and analytical chemistry. I really enjoy all things chemistry. So any questions you may have, always love to talk about them. But let's get started into our material. Chapter 0, the analytical process. So how important is analytical chemistry? Analytical chemistry is one of our 5 main branches. If we think about what we think of as like the 5 core branches of chemistry: biochem, chemistry of the body; organic, chemistry of carbon; inorganic, the chemistry of everything but carbon; physical chemistry, which is the math; and finally analytical. I like to call it the what chemistry. Basically, it provides the data needed to answer questions and test hypotheses. So it's utilized by just about every type of scientific division. And if you think about what's the most guaranteed way to get a job, analytical chemistry is really your way because it's just used so often. And no matter what you do, whether you're a synthetic chemist and you're making new compounds like polymers for detergents or stuff, if you are making new biological um, medicines, like everything about the RNA stuff that we've just made, the wonderful new vaccines that have been developed, anything really, analytical chemistry is going to play a part because we want to know how much, how many, what's actually in there, right? And that's it's such an important thing, you know. So then going into this, you want to formulate question or hypotheses, right? If thinking about our actual process or do this, we want to figure out what it is we're asking, right? There's these things that say, what is controlling this? What are we making in the reaction? What are the side products in the reaction? Can we make the reaction go faster? How pure is our product? And then we're going to select the analytical procedures because there's always a way to measure things, but you just have to think, A, I asked my question, and B, what am I actually trying to measure? So C, what instrument or analytical technique can I use to make that happen, right? So an example, so I'm working with my kids right now talking about kinetics. If you think about a reaction, say that's an acid-base reaction, and you want to measure the kinetics, ask yourself this quick question: how could I measure the rate of an acid-base reaction? You know, a couple of my students had some basic ideas, but at the end of the day, the easiest way to think about this is how exactly do I measure it? Is well, what's happening in an acid-base reaction? In an acid-base reaction, an acidic proton is reacting with some type of base, right? A proton acceptor. And so if you can think about it, we are changing the concentration of our protons on hydronium. Therefore, for changing the concentration of protons, we are changing the pH. We can measure the pH of the reaction to measure this rate. And that would be an example of sitting down thinking, what am I trying to measure? What tools can I use? All right. And then you do sampling. You run your tests. You do what you need to do. Like if you're measuring pH, you take your pH samples. If you're doing a measuring the calories in food, you do your bomb calorimetry. You do whatever you need to do to make that happen. You do your sample prep, meaning you are going to get your samples ready. If you need to dissolve it in a certain solution, if you need to run it in a certain solvent, if you need to do whatever, this is when you do your sample prep. You do your analysis, meaning you get your analysis and you figure out, I am going to run it through instrument X, instrument Y. I'm going to do mass spectrometry. I'm going to use NMR. I'm going to use IR. I'm going to use FTIR, whatever you need to do. And then you are going to get your data and you're going to go through it and you're going to interpret it. You're going to say, what does this mean, right? Sometimes when we get our data, it's very easy to look at. We get a nice spectra. We get a nice spectrum that shows peaks, like if you think about NMR or things like for IR. If it's something like mass spectrometry, we see mass, peaks, and we interpret what's there. And so you're going to get your results, and then you just have to interpret what's happening. And then once you figure out, if I mixed A and B, I got C, I think this is happening. And this is where you just figure out, you try to figure out and account for what's happening, right? So you did something, you ran a test and got results, and you just try to make the sense of it. And you make a conclusion based on the results. And so then what will happen is you go back and try to refine it and say, well, if this gives me C, then this might give me D, this might give me E. You go back and you repeat it. You change things and see if this is true, right? And this is always an ongoing process, right? So there's never a simple solution of, yes, I have the right answer. I know that this will always be right. It more often than not takes a lot of research and development before you get to things that actually get the products that we need. All right. Next up coming into is our units. This is very important. So SI, standard international, the French thing, if you remember from olden times, and you probably don't, but the world used to have very weird systems. The US is one of two nations left that still uses the imperial system. Makes no sense when you're thinking about converting, right? Like, why in goodness sake are there 12 inches in a foot? There is, 5,280 feet in a mile. There's, 3 feet in a yard. It's so arbitrary, right? It's just, there's no rhyme or reason to it. If you think about, there are, how many teaspoons are in an ounce, how many ounces are in a cup, how many cups are in a quarter, in a liter, so on and so in a quart, in a liter, and so on and so forth. Then you think about dry liquid measure, dry measurements, liquid measurements, and these imperial systems just didn't work. So finally, French scientists had the idea: what if we just make standard system based on the power of 10? And this is what happens, right? It's so much easier now because now we can just simply use prefixes. So if we think about having our standard units of mass, the kilogram, volume, the liter, temperature, Kelvin. And so if you're thinking about analytical chemistry, having these conversions makes your life so much easier. It's so much easier to do. If you've done any type of chemistry, you're in a 520 class, I know you know how to do this, but here are the prefixes that will pop up. in the course of this class. So again, just go ahead and do that. I always like to point out that it's always interesting when you try to go and try and figure out, deduce the method for how things work, how these measurements came about. My favorite is the units for temperature, because if you think about Fahrenheit, named after Lord Fahrenheit, then finally someone said, well, this makes no sense. It's based off mercury and a thermometer. What if we just used how water is? We said when water freezes here, we said when water boils 100, bam, it's named after Lord Celsius. And then finally said, well, what if we just said it after the actual energy? Because temperature is a measure of kinetic energy, the average kinetic energy. And of course, it's Kelvin, named after Lord Kelvin. So all of our temperature units are named after lords, which is just an interesting side fact. But know these things. All right. So next up here on our hit parade is that we want to make sure that we are talking about chemical concentrations. This is a general skill that you want to make sure you have. So this is the key definitions that you should take away from here. So a solute, this is the minor species in a solution. So if you think about making a solution of, salt water, your solute would be salt. Solvent is what you're dissolving into. It is the major species. So if you think about making salt water, salt is your solute, water is your solvent. Concentration, how much solute is in that solvent? There's numbers of ways we can represent that. Mole, that's an Avogadro's number of particles. This is our standard unit of how many. So if I have a mole of something, I have that many atoms, that many molecules. Don't forget. Molarity, it's a way to measure concentration. That's moles per liter. Molality, that's moles per 1 kilogram of solvent. So that is a different way to do that. Atomic mass, that's grams per mole of element. So if you look at the periodic table, look at carbon, that's 12.011 grams per mole. And that's basically how you read that. Molecular mass, you just add up the mass of all of the elements that are in there. Formal concentration, moles per liter of electrolyte converted to other species. This is going to come in a little bit later when we get into our electrochemistry. And then formula mass, sum of atomic masses of atoms in formula. And so here are some key things. If you know all of these terms already, you are in a much better position than you need to be. You're great. If not, just go ahead and review and make sure you have these. All right, so now, one of the important skills, probably the most important, maybe top 3 equations you're going to need to know for this class. Preparing solutions. We prepare solutions all the time as analytical chemists, as an organic chemist, as a whatever chemist. So here is one of the most important formulas. CV, so C1V1 equals C2V2, or C, the concentration of my concentrated solution times the volume of my more concentrated solution equals the concentration of my diluted solution times the volume of my diluted solution, right? This is quite possibly one of the most important things you need to know. It is always going to pop up. Even when you're out of this class, it'll keep popping up. I'm sure you guys have probably seen it numbers and numbers of times. So here's a practice you can do. Prepare 300 mils of a 0.1 molar HCl solution from concentrated HCl. I always like to point out, you just need to know which one is your concentrated, which one is your dilute. So I'm going to leave you guys to do this on your own. And as like I said, I will make sure that I post the answer keys at a later point. So if I was to write this is my concentrated molarity, right? And then these are going to be dilute molarity and dilute concentration, right? So I apologize for those weird lines popping up like that. But basically you can see that. You just need to figure out what's my concentrated, what am I solving for, right? Then it just simply becomes algebraic rearrangement. So go ahead and worry about that. Another thing to make sure when you're doing these, a lot of people try to convert stuff to liters or whatnot. It doesn't matter what volume you are using, just as long as you're consistent. So it says, prepare 300 mils of a 0.1 molar HCl solution from concentrated HCl. And so basically, you're trying to solve for how many moles of concentrated HCl you need. So all you would need to do then is just plug in your numbers to your algebra and you're going to get an answer in milliliters, right? So it doesn't matter what units you're using because they should cancel. So just as long as you are consistent with your units, and that's it. So if you use mils at the start, just know that your answer is going to come out to mils. If you need it in liters, do your math and then convert. So don't forget to do that. And again, I will post answer keys for this so you guys are good to go. All right. Next up on our hit list, determine, here we have, sorry about that, determine molarity and molality. So if you remember, molarity was moles per liter, molality was moles per 1 liter for 1 kilogram of solvent. So a solution with a final volume of 500 mils was prepared by dissolving 25 mils of methanol in chloroform. So calculate the molarity. So we need to know the mils of methanol. We have the density there. And then we need the solution density find the molality of methanol. So don't forget to go back, check your definitions. These are two important skills. And again, I will post answer keys in a couple days so you can see them, but I like to give you guys time to think about this. Um, Percent composition. Percent composition is an important one. Weight percent is mass of solute divided by mass of total solution or mixture. So that's the mass of whatever you're dissolving divided by the mass of the entire thing. And then volume percent is volume of solute divided by the volume of the total solution. These are two very simple things. Parts per million is grams of substance per, 10 to the 6 or million grams, and parts per billion is grams per substance per, 1 billion. So however many parts per 1 billion, we can do this grams or whatnot. So this is an easy way to do that. It's very useful to do when we think about concentrations, and we think about contaminants in, like, say, water systems, right? Parts per million, parts per billion. Typically, we want those to be lower depending on what we're doing, but these are two things you should know. And then finally, this is one, if you are from my family is from the Navajo Nation in northern Arizona, and this is something that is a major concern due to all of the mining of the uranium used for the war effort in World War II. And since most of that comes from ore called pitchblende, which you find in northern Arizona. So the concentration of lead in water delivered by Dr. V's former favorite drinking fountain is 0.252 milligrams per liter. This is the lead concentration. And so now, what is the lead concentration of molarity? How many lead atoms per gallon? And so the lead drinking water standard is currently 15 micrograms per liter. Does this fountain violate the standard? So you can think about it. There's 3 questions here. One, you should be able to do right off the bat, but does this fountain violate that standard for the maximum amount of lead you can have in your water? And so go and do that. And there it is. Picture of that. All right. So now into chapter 2, we finished chapter 0 and 1, tools of the trade. You're only as good as your tools, and if you only know how to use them. A lot of my siblings work, as a plumber, carpenter. They are craftspeople, and like they always tell me, and thankfully they taught me some of these things. My brother who's a mechanic as well, is that you're only as good as the tools you are using. You can only be as confident and comfortable if you know how to use everything you're using. So as a chemist, that's especially true, right? If I need to run an analytical test and it's the first time doing it, I'm going to go find a professional, someone that has used it before, someone that can show me and explain to me all the working parts. And this is no different from you guys. So I'm sure all of you have done this to some extent. And so when we think about this, safety first, right? Primary safety rules from Harris: to familiarize yourself with the hazards and do nothing that you or your instructor or supervisor would consider to be dangerous. This is true in everything we do. Always be safe, always follow the rules. And not only be familiar with hazards, think about how the hazard could be mitigated if an accident or problem arises. Also be familiar with hazards present in the lab that are not associated with the experiment. Now, this is something we're not necessarily going to be doing because we're not doing in-person labs, but if for those of you that are working in the industry, I always, when I teach my undergrads and the undergrads that I mentor in my lab, is that, the whole idea of taking time to read what you're using if you're using something new, prepping for the worst case scenario beforehand, doing everything you need to do, mitigating all these possibilities, not only mitigating I'm going to clamp bottles, I'm going to use safety lines, whatever you're going to do, but then also thinking, in case something bad does happen, what can I do in case the worst scenario happens so that I can help minimize that? An example, if you use sodium borohydride as a reducing agent, very useful, but if it catches fire, it's hard to put out unless you have sand. And so whenever we use sodium borohydride in lab, we typically have a beaker of sand ready to throw on it in case we need it. And this would be an idea of, you're taking all of these precautions, you're using it correctly, but you're always prepping for just the worst case. And so then laboratory notebook, and again, we're not going to be doing this necessarily, but I always like to throw this in here, is that always state what you're doing, what you're setting up. State what you observe, change color if it heats up, bubble, whatever. Be understandable to someone else. Your notebooks need to be legible in all purposes, right? And this is something I always harp on, even when I'm not teaching the lab, is that a reminder that your lab notebook is essentially a legal document, meaning worst case scenario, you set up an experiment, you go in, something happens. Maybe the reagent wasn't the grade you thought. Maybe there was an accident on your end or someone else's end. Your lab notebook becomes a legal document of what happened, right? So it needs to be not only written well, but it needs to be legible. And also, if you're doing anything and you need to go back and check your notes, whatever, you want to make sure that you can read it. So, this is one thing I always harp on. And again, graduate level class, I know you guys are probably excellent at this, but I always just like to remind people the more detail you can do in the notes, cleaner they are, the better. And it's just important because it'll help make sure that whatever you're doing, you're following it. And if you need to, tweak an experiment, you can go in and say, well, here's what I did specifically last time. What can I change this time, right? And so safety is always important. If you're going up to wine country, even those of us who may like to have the occasional wine, safety is always important. So it's always good to keep that in mind. Another thing that I always like to remind people measuring mass, this is more of just understanding the lingo. Weighing is a misnomer. We don't weigh things, we mass them. So mass equals the amount of matter, whereas weight is gravitational force. So, your mass is constant no matter where you are in the universe. Your weight changes depending on where you are in the universe, right? Like your weight would be uh, less on the moon, right? But you still have the same mass. And so measurement mass is the most basic measurement in chemistry. And so there's one of our nice little analytical balances that we use at GCU. For those of you that have taken a chemistry class, we have a couple of these. And so you can see that it goes to the 10,000th place. Very excellent little instrument. And you can see we can keep it closed and almost everything. So when we mass things, we can be very precise. And then types of balances, you have top loading balances that can do a gram, 10th, 100th, or 1,000th gram. These are, for freshmen and sophomores in general chemistry, we always like to use these ones because they're more forgiving, they're easier, they're not as expensive in case someone damages it. But then you can get some analytical balances that go down to the 10th or 100,000th. They're really great at being precise. You just have to be careful. And then you have microbalances that can go to the microgram or less. Those are very tricky to use. You have to be careful. And here are just like, some ideas of having some top loading ones. And then there we have that microbalance there. You can see that it is very well fine-tuned. It's been calibrated excellently. And it's just, depending on what you're doing, you need a more precise balance. And it just depends. But these are just some ideas to think about. And standard masses is something always good to introduce. Balances are calibrated by comparison to mass standards, which are hopefully traceable to NIST or equivalently certified standards. And essentially, it is just a box. We use standards that are made out of metals that don't degrade over time, so the mass stays consistent. They've actually recently, and I want to say in the last 2 years, they developed a way to calibrate mass without using these standard balances, right? If you think back to the original days of when they first created these standards, the metric system, essentially they would make a kilogram, essentially this type of like spherical bell object. And I can't remember what the metal was made of. It might have been tungsten. I forget off the top of my head, but essentially the U.S. ordered one. I think it's probably Thomas Jefferson. He would have been the guy, or Ben Franklin. And the ship that was bringing it over sunk. So maybe our country could have been a metric system at some point. But you just have these types of things that you can use to calibrate. So if you are a calibration person, if you're someone that does this, you probably have this small system. Someone will come in and do this to our balances once a year. They charge a lot of money, but that guarantees that our instruments are up to, they're up to code and everything else, and makes life easier. All right. And so then something else we're going to talk about here, the buoyancy problem and correction. So if you think about this idea, right? So the measured mass of an object is less than its true mass based upon the mass of the air the object displaces. So when we think about, and I'm going to hit pause real quick. Sorry about that. There's a fire truck going by outside. I live close to a firehouse. But one thing, this is something that you may not have ever considered, but if you're a good analytical chemist, maybe you've talked about it, is that when we think about you saying, I'm going to go balance something, but don't forget, there's atmosphere above you, right? There's atmosphere everywhere if you're on the planet Earth. And that air has a mass, right? And we can think about this in terms of air pressure. So when you actually go to place an object on a balance and you go to mass it, the actual measured mass that you're doing, it's less than its true mass because you're displacing air. It's just the weird thing that happens because you are displacing the air of the object being there. And so our mass is not going to be different. You can think about this in the idea of having like a iceberg that's floating in water, that most of that iceberg is below the water line, things like that. So it also affects comparison masses when we think about the weights of things. and the density of the objects of comparable weights. All right, so we can do a buoyancy correction, and basically our true mass is going to equal the measured mass. So whatever we measured on our balance times 1 minus the density of air divided by the density of our weights, that whole thing divided by 1 minus the density of air minus the density of the object. And so we can just plug in our numbers for this, so we can actually do a buoyancy correction when we're actually measuring mass. This is useful if you need to be very precise, right? If you accuracy is key. If I'm just doing an experiment where I mix things in a Gen Chem lab, right, and I just need to see a color change, me doing this correction is a waste of time. If I'm doing something to where I'm trying to get the water levels just fine for human consumption, and I need to make sure that the mass of what I'm weighing is correct so that it gets my desired chlorine and other magnesium and other, ions that need to be correct in water correct, then I will do these corrections, right? And so the more specific and accurate I need to be, the more often these come in. So in the world of analytical chemistry now, this is very important. So I'll write this down. And so it's going to take this information. And so here we go. 25 milliliter class A pipette is calibrated by quote unquote weighing the water delivered in a tared open beaker. Right. So essentially you just take a 25 ml pipette, you uptake 25 mils, however it says, and then you transfer it into a tared open beaker. And then you figure out, so the measured mass of the water is 24.9326 grams. What is the true mass of the water? So there we have the density of air, we have the density of water, and we have the density of our weights. So then you would just go through, you take those values, right, and our actual measured mass is 24.9326, and plug it into this equation. And so then that would be another one that you guys should practice doing. It really is just a plug and chug. I'm gonna hit pause again because there's more fire trucks coming. I apologize. Okay, so go ahead and do those problems. That should be it. And that brings us to the end of our chapters. Hopefully that offers help. And again, don't forget you have homework that's been assigned for you guys. If you have questions, send them to me. I'm more than willing to meet with you guys online to have a Zoom session like this and to talk about it. And I really hope that we have a good course. I think we only have 8 weeks of class time, but just message any questions. I'm looking forward to it, maybe 7 weeks. And next week's PowerPoints, I'll start including the ideas about the presentation and paper you guys need to do, just so you guys can start thinking about it. But I hope you guys have a good rest of your weekend, and great to meet you. And I look forward to this class, and have a wonderful rest of your day. Bye, everyone.